So today we're going to do a demonstration of eddy current breaking, which is Faraday's law in action. So what do we have here? I have a copper pendulum swinging back and forth, just like in 801. If I make it swing, there it is, swinging back and forth, perfectly ordinary pendulum. Just have a look at this. If you look at this piece of copper, this is just orange paint, so you can see it more easily. And it's suspended here, and it's swinging back and forth, and there's nothing interesting going on until I power this magnet up. So this is an electromagnet. Right now, the switch is open, so there's no current in it. But as soon as I power the magnet up, look what happens. That thing can't swing anymore. It is as though I put the brakes on. Here we go. Remarkable. So this is eddy current breaking. I'm going to explain to you what's actually happening. But before I do, think back to the demonstration that we did a little while ago where we dropped magnets through two tubes. One of them was plastic, it's not a conductor. The magnet fell through it like normal. And the other one was a conductor, and the magnet fell through very slowly. That was another example of eddy current breaking. This one, though, is sort of one of the classics. I'm trying to move this piece of copper through this magnetic field. There's a big, strong magnetic field here right now, and it just comes to a stop. So, in fact, I can try and fling it through. Here we go. I'll try and fling it through, and it won't go through. I have to really pull it through to get it through. Same thing from this side. It just won't go through. It will not move through easily. It's like it's in molasses. I can't see the molasses. The molasses is coming from the magnetic field. So let's try and understand what's actually happening here. So what I want you to do is I want you to think of a loop in this copper. And let's think about this loop as this particular loop in the copper comes into the magnetic field. So this loop in the copper right now has no magnetic field in it. And as it swings in, well, now it has a big magnetic field in it. And so as that happens, there will be a current induced in this loop. And what is the effect of that current? Well, let's suppose that this is the North Pole side of this big magnet, this is the South Pole side, so the big magnet is making a field going that way. Faraday's law tells me that when this loop swings into the field, there'll be a current induced that will try to oppose the field that the big magnet is making. So the loop is going to make a field going back this way. And if the loop makes a field going back this way, that means this loop of current in this copper is now behaving like a magnet itself with its north pole on this side. And so now I have north repelling north, and that repulsion is slowing the motion of the copper down. Now, let's think about a loop on this side. Okay. As that loop is, right now it's in the field, and now it's coming out. As this loop starts out with a big field in it and comes out, the field through this loop is getting less. If the field through this loop is getting less, then the current in this loop will be set up to make this loop a magnet which tries to make more field in the same direction to prevent the field from getting less. So that's going to make a magnetic field pointing this way. And now I have north attracting south and south attracting north. So on both sides, the loop that's going in and the loop that's coming out, I'm getting a magnetic field being generated. And that magnetic field is, in both cases, opposing the swing of the pendulum. So let's see this again. First of all, let me remind you how an ordinary pendulum behaves with no eddy current breaking. Here we go. Okay. And now as soon as I put current through the magnet, there is now, when this piece of copper tries to go through the magnet, there are currents being induced in the bit of copper that's going in and in the bit of copper that's coming out, and both are set up in such a way as to oppose the motion. And so the result is that it looks like it's in molasses, as you just saw. Here we go, one last time with this, in molasses. Okay, now, to convince ourselves that that is the right explanation, I'm going to next do the same experiment, but with this pendulum. So let's have a look at the difference between these two pendula. This is the one we were using before, and now this is the one I'm going to use now. And you see that the difference is that this pendulum, the copper is sliced, it's perforated. And so in this piece of copper, you can't have big loops of current flowing because there are all these cuts. You can only have tiny little itty-bitty loops flowing inside each little strip of copper. You can't have a big current flowing. So let's see how different this is. If it's different, let's find out. So here we go. So first of all, no current. This is a pendulum like any other. And now let me do the current. And what you see is that it did get slowed down. Watch it again. It is being slowed down, but the slowing down effect is much less than before. It swung back and forth about half a dozen times before coming to rest instead of just coming to rest immediately. So here we go again. It is being slowed down, but the effect is less. And I'm going to open the circuit, remind you how this looks normally. And you can see that in comparison to this, when I had the electric current flowing, it was being slowed down, so there is some eddy current breaking, but much less because the big loops of current in the copper that were flowing before can't flow in this one. Let's do one last comparison. So here we go. Ordinary pendulum, no current. Turn the current on, and it comes to a stop after a few swings back and forth. Now we'll try the other one. No current flowing. No current flowing. It's an ordinary pendulum. Now I turn the current on, and boom, comes to a stop. So this one has much greater eddy current breaking than this one, because in this one you can set up the large loops of current, whereas in this one you can only get small loops of current.